Hello, good morning all. Uh, as you are aware that we are doing Matrix Algebra, and in today's lecture we are going to do some previous year questions on Matrix Algebra. Uh, we are coming to the end of this topic. Most of the things have been discussed. Most of the PYQs have also been discussed in detail. And I hope that you are liking these lecture series. And I hope to start linear algebra after having such strong foundation. Okay, so let us begin with the question that I left in middle um, in one of the class. In one of the class, actually, when I was solving this question, all of a sudden I actually did take a break, and I told you that okay, this question would need certain more ideas regarding diagonalizability. And since now you have done diagonalizability, now let us write a few more things that you should remember. Okay, and let us start with this question. Okay, so in this question, it was given that A is a 4 cross 4 matrix. A is a 4 cross 4 matrix with real entries such that minus 1, 1, 2, and minus 2 are eigenvalues. The first thing that I told you that if an n cross n matrix, if an n cross n matrix A, let's say A, has n distinct eigenvalues, n distinct eigenvalues, then it implies what? Implies that A is diagonalizable. A is diagonalizable. Diagonalizable. Okay. The first thing that you should know, I think that I have already dictated that if a matrix A, because see, if it has n distinct eigenvalues corresponding to these n distinct eigenvalues, you can always generate a n set of linearly independent eigenvectors. Now, if you have n set of linearly independent eigenvectors, then it is quite clear that the matrix A would be diagonalizable. And we also know that if A is diagonalizable, so is A square or A raised to power 4, so on and so forth. Is that clear? I think it is clear. So if A is diagonalizable, then A raised to power 4 is also diagonalizable. I told you that let's say if for A we have some matrix, let's say D, and this is how you can represent it. Then it is quite clear that A raised to power n can be written as P inverse D raised to power n P. Okay, so if A is diagonalizable, so the higher order powers are also diagonalizable, right? Higher order powers to the A would also be diagonalizable. So A raised to power n would also be diagonalizable. Is that clear? Okay, and now just think about B. Okay, so matrix B. Okay, so matrix B would also be diagonalizable by this logic. So if I say that what is B? B is equal to A raised to power, I think some 5 or something, A raised to power 4 minus 5 A raised to power 2 plus 5 identity. So this would also be diagonalizable. So B must be diagonalizable. Now there is an important result that you should remember. An important result that I'm writing, you should remember. If it so happens that if A and B are two matrices, if A and B are two matrices such that both of them are diagonalizable, okay, such that both A and B are diagonalizable, and both commute also, and both of them commute. Both of them commute. If A and B are two matrices such that A and B are diagonalizable and both of them commute, then these matrices are called as simultaneously diagonalizable matrices. So I will say that both of them are simultaneously diagonalizable matrices. Now, what is the benefit of having simultaneously uh, diagonalizable benefit? What is the benefit of having simultaneously diagonalizable matrices? So, if in that particular case, if A is having some eigenvalues, let's say lambda, and B is having some eigenvalue, let's say omega, then the eigenvalues of A plus minus of B would be nothing but it would be equals to lambda plus minus of omega. This is one of the very important things that you can remember right now. I'm not going for the proof. I'm just giving you that if A and B are two matrices such that both A and B are diagonalizable, which in our case is yes indeed. So you know that your A is having four distinct eigenvalues and B is represented in terms of A. So I can say that uh, B is also diagonalizable. And further you can see what would be AB. AB would be equals to A into A raised to power 4 minus 5A square plus 5 identity. And similarly, if I want to write BA, so I can write it as A raised to power 4 into A minus 5 a square into, sorry, here I'll get A here, and then I will write 5 times identity into it. So clearly I can say that my AB would be equals to BA. It implies what? It implies both matrices A and B commute each other. So if A and B commute each other and both are diagonalizable, then their matrices are additives, and obviously you can subtract them also to find the eigenvalues of A plus minus of B. So for corresponding to eigenvalues of A plus minus B, this will be answer. Is that clear? Now you see, I already know that the eigenvalues of A are minus 1, 1, 2, and minus 1. And how is B related to A? B is related to A by this A raised to power 4 minus 5A square plus 5 identity. Is that clear? I hope it is clear. Okay, so if this is the case, then if you want to find the eigenvalue of B, eigenvalue of B would be, if I place eigenvalue, so this will be solving the characteristic polynomial of lambda raised to power 4, and this here I'm writing eigenvalue of A minus 5 times lambda A whole square plus 5. Now if I place this, so eigenvalues of B will come out as 1 minus 5 plus 5, this would be simply 1. Then you can write again, if you place 1 here, so you'll get 1 minus 5 plus 1, so it is again 1. Corresponding to 2, you will get 16. 16 minus 10, 16 minus 20 is minus 4, and again 1, sorry, and identity again by 1. So eigenvalues of B, the set of eigenvalues of B would be 1, 1, 1, 1, 1. Now what has been asked to you, the question that has been asked to you is, what can you say about determinant of A plus B, determinant of B, trace of A minus B, and trace of A plus B? So let us do. So what do you think the eigenvalues of A plus B would be? I told you, if the eigenvalues of B are omega and eigenvalues of A are lambda, where it has gone, then eigenvalues of A are lambda, then we can add them up to get the eigenvalues of A plus B. So if I want to find the eigenvalues of A plus B, the eigenvalues of A plus B would be what? It would be simply, so I'm adding them up, so it will be 0, I'm writing eigenvalue of a plus b. Eigenvalue of a plus would be 1, it would be simply 2, it would be simply 3 here, and it would be again, I think 0, or I think again 0 it should be, right? Achha, last one was -2, my mistake, sorry. So again, for -2 also, because these are all even parts, I'll get 1. So in any case, this will be like -1. I know that if I'm even having a single thing as 0, even if I'm having a single thing as 0, then I can say that my determinant of a plus b would be 0. Why? Because determinant is nothing but the product of eigenvalues. It is equals to the product of eigenvalues. If it is the product of eigenvalues, then what I can say, since one of the eigenvalues is 0, so determinant of a plus b would be 0. What would be determinant of b? Determinant of b would be 1 because all the eigenvalues are 1. So product of eigenvalue again 1. What do you think the trace of a minus b would be? So trace of a minus b would be, if I have added, if I add them up, if I subtract them up, then I will find the eigenvalues of a minus b. So eigenvalues of a minus b would be what? It would be -2, would be 0, 1, and -3. If I want to find the trace, it means sum of all these things. So if I sum them up, I'll get minus of 4. So trace of a minus b is minus of 4, which indeed is not present. The option that has been given to you is that trace a minus b is 0. And if trace a plus b, if I have to find, what would you trace a plus b? It will be sum of eigenvalues here. So the sum of eigenvalues here is 4, and which indeed is the case. So clearly option number A, option number B, and option number D are correct option. I hope you've got it. I have just mentioned one statement that you will have to remember. I'm not going for the proof right now because that will be a hefty proof to do. But always remember this simultaneously diagonalizable matrices are quite important for us. I hope it is clear. If there is any doubt, please you can ask me for that matter. Okay, so I hope it is clear. Should I go ahead? Okay, so this is a theorem. So it's a kind of, you can say, a result that you should remember. Okay. Okay. Now let us go to further. Okay. Okay. So now let us go to a few more questions. Okay. So today uh, I'll take more questions on from the previous year papers only. So this was one of the questions that I left somewhere. So I think I thought it is good to start from here. But just remember the result because it will be very difficult for you to right now because we are having the last class. So I want somehow that are most of the things get finished today. Okay. So we've done quite amount of questions. Now we'll start with. I think it should be give you a difficult one. Okay. So question states that I think this is something that I have already done, but with determinant 1, they should have not even written determinant 1 because determinant 1. Okay, option number 1, the modulus of each eigenvalue need not be 1, but their product must be 1. Their product must be 1. Another option, option number B, says that at least one of its eigenvalue is plus 1. At least one of its eigenvalues is plus 1. Option number C, all of its eigenvalue must be real. All of its eigenvalues must be real. Given to you is none of its eigenvalue is true for 3 cross 3 orthogonal matrix. Okay, so I think this is quite easy question. We have done great results on this thing. Already we have done a good amount of questions on your what should I say, eigenvalues and this thing, eigenvalues and eigenvectors for orthogonal matrix. So this is directly a property based question. So let us do this question. Okay, now in order to do such questions, just think about some matrices. So I have already taught you the rotation matrix. If you remember, we have done rotation matrix, right? We have done rotation matrix, and we know that for rotation matrix of order 2 cross 2, the eigenvalues are 1 and e to power iota theta, and for a rotation matrix of 3 cross 3, I know the eigenvalues are 1 iota theta and e to power minus iota theta. In fact, we have also seen an orthogonal matrix called as a reflection matrix, and reflection matrix had a property that its determinant is minus 1, and for rotation matrix we had a property that its determinant is plus 1. In fact, we also derived that if a matrix is orthogonal where A transpose A is equal to identity, where A transpose into A is identity, we know that the eigenvalues are unimodular. If you remember, just before unitary matrices we derived this result that if you have a orthogonal matrix, then the eigenvalues should be unimodular. If you remember, the eigenvalues must be unimodular. Determinant of A and determinant of A transpose are same. So you will get determinant of A whole square is equal to 1. So it implies that if you have a unitary matrix, if you have a even if for unitary matrix the eigenvalues must be unimodular, and also that determinant can be either plus 1 or minus 1, which I have also explained you by taking example. And eigenvalues also you can see. So none of its eigenvalues need to be real. So none of eigenvalues need to be real means what? Not even one eigenvalue can be real. See, here it is. So this option is rejected. All the eigenvalues must be real. Again, this option is rejected by taking these two examples. Modulus of each eigenvalue need not be 1, but you can clearly see that each see, this is true for all the orthogonal matrices. It is said that okay, instead it was taking 3 cross 3, so let us just discuss 3 cross 3. So if it is true for all 3 cross 3 matrices, let's say if all these 4 statements are true for all the 3 cross 3 orthogonal matrices, then it should be true for some specific orthogonal matrices also, right? So for a specific orthogonal matrix, I have selected a rotation matrix, and I know the eigenvalues to the rotation matrix are 1, e to power iota theta, and e to power minus iota theta. If that's the case, I know that modulus of each eigenvalue should be 1. The answer would be at least one of its eigenvalue is 1. At least one of its eigenvalue should be 1. I guess answer should be B. So I think this is easy question for you. That is why I have in detail discussed eigenvalues and eigenvectors to each of your special matrices, right? If you remember, we made a diagram also where we concluded our findings. Is that clear? Okay, now let us do a few more questions and see. So question was, it's quite easy. Again, it was given in net exam only. So let us take another question from net exam. The question says that one of the eigenvalues one of the eigenvalues of the matrix R. This was asked in net exam. So if you remember, whenever one says what is the product of eigenvalues, I know it is equals to determinant. So determinant A, let's say in general A, and not this A I'm saying, determinant of A is equal to product of eigenvalues of A, right? So determinant of A is equals to product of eigenvalues of A, right? Now you see, instead what has been given to you, it has been given to you that one of the eigenvalues of e raised to power A is e raised to power small a. So remember, yesterday we sort of you can say I gave you a small proof. However, I did not explain the Jordan canonical form, but that we'll do in our linear algebra course. But remember, if I want to find the determinant of e raised to power some matrix, it is equals to determinant of e raised to power some matrix A. It is equal to e raised to power trace of that matrix, if you remember. Okay. Now it has been given to you that one of the eigenvalue is e to the power A. Okay, so let's say the other two eigenvalues, let's say I'm writing lambda 2 and lambda 3, and I know that my lambda 1 is equal to what? Lambda 1 is equal to e to the power A. So my lambda 1 into lambda 2 into lambda 3 should be e to the power of trace of A. And what is trace of A? It is equals to A. What does it imply? It implies e raised to power A into product of eigenvalues, that is lambda 2 into lambda 3 should be equal to e raised to power A. E to the power A cannot be 0, so I can cancel this up. It implies that the product of two other eigenvalues should be equals to 1. So that is what I keep telling. Whenever you are studying for net exam, just keep focus on what JEST and TFR and other such examinations are asking you, because most often you'll find that some concept that has been asked in TFR examination may get a repeat in net examination, or vice versa. If some concept has been asked uniquely in net exam, it may get repeated in TFR exam also. So please keep that note. I hope it is clear. Okay. Now another important question that has been asked in GATE exam. Now I'll give you that question, and probably that is another question that you should look at. The question says, this was asked in GATE exam. Okay, the question says that for a rotation matrix, this that is given to you 0, 1, 0, 0, 0, minus of 1, and then you're given minus 1, 0, and 0. The unit vector along the axis of rotation. Unit vector along the axis of rotation would be, I'm not giving the options, just try to find that what would be unit vector along the axis of rotation. So always remember that, let's say I'm rotating about, let us say I have a tetragonal. I have a tetragonal. Okay. and let us say that I am rotating about this axis. Okay, let us say I am rotating about this axis. Okay, so what remains invariant? So I can say that during a rotation, the axis of rotation, that is axis of rotation, remains the same place. Okay, so axis of rotation remains unchanged. Always remember this. So during the rotation, the axis of rotation remains unchanged. Okay, so what does it imply? It implies that if my axis of rotation vector, let's say axis of rotation vector, if I assign it, let's say x1, x2 and x3, and since I have to find the unit vector, so obviously I'll do this x1 square plus x2 square plus x3 square. I'll divide it by this particular thing. That is quite easy to, I mean, that I'll do later on. So okay, this I'll do later on. I'll normalize it, don't worry. But overall it is asking that if I talk about, so even if it is rotated through because of this matrix, so under this transformation matrix, the rotation axis remains invariant. Okay, so I'll write it here. Under the rotation matrix transformation, or you can say rotation matrix action, the you can say the rotation axis remains the same. Rotation axis remains the same. And so what I can write that if this is my transformation matrix, let's say what it was given, it was given 0 1 0 0 0 and -1, and it was given -1 0 and 0. And then what you can do, you can place x1 x2 x3 here, and under the action of this particular rotation matrix, this should remain simply x1 x2 x3. Otherwise our case would be violated, because what we are saying, that under the rotation, the axis of rotation remains unchanged, because that is along that particular line only. Is that clear? That's very much clear, that if I want to rotate this tetragonal along this axis, so this axis would remain in, this axis would not rotate, right, in any way. So so if I do this, what I'm getting x1 here, I'm getting, I think, minus of x3, and here I think I'm getting, oh, this is x2, sorry, and here I'm getting minus of x1, right? And this should be equals to what? This should be equals to x1 x2 and x3, right? What does it imply? It implies that your x1 should be equal to what? X2. Your x2 should be equal to what? Minus of x3. Your x1 should be equals to what? Minus of x3, right? So if I take x1 and x2 as 1 1, so I take, if there's a 1, so this would be -1, and if I normalize it, I can place a 1 over root 3. So this would be unit vector along the axis of rotation. I hope it is clear to you. Okay, so this was an easy question, but the concept is important. Please keep in mind the concept. However, in the exam it was given that axis of rotation remains unchanged, but actually I withdrew that particular line because I wanted you to think over it. Okay, now let us go to a few more questions and then we'll conclude this lecture. Okay, so this we've done. Gate question also we've done. Okay. A few questions I'm leaving it for you as an exercise that we'll see once. Uh, okay, so once we'll be doing another discussion lecture, I'll do that, those things there. Meantime, I would insist you to revise each of these concepts very nicely. Okay, now you see there's a question that was asked in JEST exam, and it is based on similarity. Oh, so question says that let a be equals to what? A is equal to 1, 0, 0 and 11, and m equals to 10, 3 iota, minus 3 iota and 2. The similarity transformation of m to a can be performed by, so can be performed by which of the following matrices. So there were 4 options given to us. I will directly we'll directly try to find the answer to this without writing the options because of the lack of the time, and it will become very tedious thing to write it right now. So we'll directly do the question, don't worry. So you know that okay, so if you remember yesterday when I was discussing with you the similarity transformation, what we wanted to how did we how to find the what you can say, how to find the corresponding what you can say eigen sorry corresponding matrix. So let's say it implies what? It implies that answer. So this is the diagonal matrix, right? So this is the A is a diagonal matrix clearly. A is a diagonal matrix. So I can write that A would be equals to what? It would be equals to some P inverse MP, right? And how to create this P? This P was nothing but it was created by, it was nothing but it was a matrix that was created by eigenvectors of M. If you remember, yesterday we did all these things. Eigenvectors of M. So the first thing that comes to mind is let us try to find the eigenvalues, eigenvectors of M. So first let us find eigenvalues. So if I solve it here, okay, why even solving this? Because see, already we know that A is the diagonal matrix. M and A must have the same eigenvalues if they are connected. So I'll write it here. Since A is similar to M, so at least we can save our time instead of finding this. Instead of, even if you want to find, that is up to you, but you know that A and M are related by the similarity transformation. So instead of finding this, I know that directly use that the eigenvalues of M would be 1 and 11. So this is something that I already know. So now directly jump on to finding the let us jump on to finding the what you can say. So let us take this 10 minus 1. Here it is 3 iota, here it is minus 3 iota, here is 2 minus 1, and here you have this, let's say x1 x2 equal to 0. What does it imply? It implies 9 times x1 plus 3 iota x2 is equal to what? 0. Okay, is there a mistake somewhere? I don't know. I hope it is correct. And the other one would be minus 3 iota x1 plus x2 equal to 0. So from here also I can get that my x2 should be equals to 3 iota x1, and from here also the same. Because here I will be dividing by 3 iota and then I will be multiplying 3 iota 1 below. Okay, so this is 1, and if I use lambda is equal to 11, what I'm going to get? I'm going to get minus 1 here, 3 iota here, minus 3 iota here, and I think minus of 9 here, I guess. Okay, and this would be x1 and x2 equal to 0. What does it give me? It gives me that x1 is equals to 3 iota x2. Okay, what does it imply? So your matrix P would be simply, I think if I write x1 as 1, then this would be 3 iota, and here if I write x2 as 1, here I'll get 3 iota. And if I want to normalize it, I can normalize it by uh, uh, like for example, if I already know, so I'm writing it here so that it's no worry for you. This is 1 3 iota, and here it is 3 iota and 1, and I can normalize it by dividing it by the modulus square and root over. So modulus square and root over, I think this would be 1 over root 10 here also, and here also 1 over root 10, because you see this is 3 iota. Don't do the 3 iota square, plus first take the modulus of it. So modulus of it, 3 iota would be 3, root square would be 9, 9 plus 1 would be 10, I guess. So the answer should be this one. Probably you may get some different answer also if you can get this way also, but overall understand uh, this is a symmetric matrix. So you, okay, so this is how you're going to get one of the answers. I hope it is clear. Okay, now let us do a few more from net also, so that okay, so there is another question where it is a 2 cross 2 unitary matrix has been given to you. So let us do a question from net exam. Let us do a question from net exam, and the question says that given a 2 cross 2 unitary matrix given a 2 cross 2 unitary matrix U satisfying U dagger U is equal to U dagger is equal to identity. Even if they have not supplied us, that was fine, with determinant that they have given to us is equal to e to the power iota 5. One can construct a matrix V. One can construct a unitary matrix V with determinant V equals to 1 from it by option number 1, multiplying U by e to the power minus iota 5 upon 2. Option number B, multiplying any single element of U by e raised to power minus 5. Option number C, so this is A, I guess. Option number C, multiplying by any row or column of U, by e raised to power minus 5 by 2. And option number D, multiplying U by e raised to power minus e to the power iota 5. So this is your question. It says that given a unitary matrix which is equal to U, and such that it satisfies the necessary condition for the unitary matrices, that is U dagger U is equal to U dagger is equal to identity. I mean, this is how the questions are written in your net exam. It is given that the determinant of u is equal to e की power iota 5, and it is asked that one can construct a unitary matrix V with the condition that determinant of V is equal to 1 from it by multiplying u by e की power minus iota 5 by 2 or by any other single element of u by e की power minus 5 and all those things. So let us directly go to the answer, how to approach it. So I don't know how to approach it, so what I would do, I would say that let us multiply u by, let's say, k. Okay, such that v is equal to what? V would be equals to k times u. Also remember, I told you that if you have a determinant of A, and let's say A is an n cross n matrix, and if I want to find determinant of Ka, it would be equivalent to writing k raised to power n determinant of A. Okay, so instead we are supplied here with 2 cross 2 matrix. Okay, now you see, I know one thing, that if I'm getting v by multiplying u by k, I know that determinant of v would be equals to determinant of k into u, right? And I know that I'm talking about what you can say, 2 cross 2 matrix, so it is equals to determinant of u. I know that determinant of v is equal to 1. It implies k square should be equal to determinant of u. And what is determinant of u? It is equal to e की power iota 5, and that gives me that my k would be equals to what? E की power minus of iota 5 upon 2. So clearly, if I multiply my unitary matrix u by e की power minus iota 5 by 2, I will get a matrix V in such a manner that its determinant will be equals to what? 1, and such that it also remains unitary. It also remains unitary. Uh, is that clear or not clear? Is that clear or not clear? I guess it is clear. Okay, and if you want to check, it is quite easy to see that V dagger V would be equals to identity. It is very easy to see. See, if you want to see what would be V dagger, V is what? V is equals to what? It is equal to k times u, and if I write V dagger, it is equals to k complement, sorry, not k conjugate, and here it will be u dagger. So it is simply, this will be equals to what? So V dagger, if I want to write, it would be e की power iota 5 by 2, and here you have u dagger, and what would be V? It is e की power minus iota 5 by 2 u. So if I take V dagger V, it is equals to similarly writing u dagger u only, and it is equal to identity. So clearly V satisfies the condition for unitary matrix, and other part has been proved to you already. I guess it is clear. If you have any doubt, please you can ask it to me right now. Okay. So there are a few more questions left. I would suggest that you go through all these questions at first, and if you find certain difficulty in any of the question, please let me know. Most of the questions that I have seen in this particular chapter are relevant to the eigenvectors and eigenvalues only. A few questions we'll discuss in the problem discussion session. That would be a separate thing. But I hope you've learned a lot from these lectures, 9 lectures of matrix algebra. I conclude my this matrix algebra lectures today, and we'll continue with one problem session probably in next week sometime. Overall, from tomorrow onwards, we are going to start with linear algebra for quantum mechanics. I hope to meet you tomorrow. Till then, take care.